The simple linear model is y equals beta 0 plus beta 1x plus epsilon, where epsilon is normal with some constant standard deviation. Here, x is 50 random numbers between 0 and 100. Y is a linear function of x plus this error term. You see the errors are 50 normal random variables with mean 0 and standard deviation 2. In this case, I have beta 0 equals 1 and beta 1 equals 2. I'm going to fit the linear model y hat equals b0 plus b1x. The output from R will give me the b0 and b1. We can see how well they estimate beta 0 and beta 1. You can see the scatter plot of y versus x. The points almost fall on a line, but the error jitters them somewhat. The output from R is that the intercept is 0.548 and that the slope is 2. I want the intercept to be 1 and the slope to be 2, so it's doing a good job with the slope, but the intercept's a little bit off. Let me run this a few times. 1.54 and 1.99. There's one that's pretty good. The intercept's just about 1 and the slope is just about 2. If I change the standard deviation of the error so that it's 0.25 instead of 2, the points cluster more tightly about a line and the estimates are better. When there's more error in the system, the estimates will be worse. Now the standard deviation of the error is 20. You see, the points don't fit the line as well, and the estimates we're getting aren't as good. But also notice that the intercept tends to be further off than the slope. The slope is coming out near 2, but the intercept is often far away from 1. Here's a multiple linear regression. Now, y will be a linear function of 3 variables, x1, x2, and x3. The linear model is y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Just as before, I'm going to have x1, x2, and x3 be 50 random numbers between 0 and 100, and y will be 5 plus 4x1 plus 3x2 plus 2x3 plus some random error term. I'll fit the linear model y hat equals b0 plus b1x1 plus b2x2 plus b3x3, and once again, I want to see how well the b's estimate the betas. I can't draw a scatter plot of these because it would be in 4 dimensions, and I don't know how to draw anything in 4 dimensions. So instead, we use a pairs plot. I need to make this into a data frame. If we look at the response, which is y, versus each explanatory, we see a strong relationship with x1, a fairly strong relationship with x2, but a little bit weaker, and then a much weaker relationship with x3. That's why you can't really diagnose the linearity assumption from these graphs, because here x1 is multiplied by 4, but x3 is multiplied by 2. X1 is the more powerful predictor. It dominates so that x3 looks like it might not matter even though it does. If I look at the explanatory variables against each other, like x1 versus x3 here, you see that they look like a bunch of random noise, and that's what we want to see. They're not correlated with each other. I want it to go 5, 4, 3, 2. And you see that's mostly what it's doing. Once again, its performance will depend on how much error is in the system. The error only has standard deviation 2 here. Here's an example with multicollinearity. We want the explanatory variables to have a linear relationship with the response, but we often don't want them to have a linear relationship with each other because then they may be redundant. Now, it depends on what you're doing, and you might want to keep some collinear predictors in your model if it improves the performance or you think it will explain the situation better. But when we have perfect multicollinearity, so that one variable is a perfect linear function of another, the math will break down. Let me draw the pairs plot. You see, I get NA for the last one. In real life, you'll rarely see perfectly correlated predictors like this, but it might happen when you try to make a variable that is a linear function of the others. Like an economist might take income, education, house size, or whatever, and make a score that's some kind of linear function of them. And if they then fit a model that has house size, income, education, and that score, the regression would turn out like this.